Okay, welcome back, everyone. Our last junior speaker for the day is Saverio Andrea Secci, and he's talking about Fano for folds having a prime divisor of Picard number 1. So whenever you're ready, start.
Thank you very much. I'm really happy to be here. And this work is a classification result about Fano varieties. And the classification of both complex Fano varieties has been completed up to dimension 3, while there are many results, but not quite enough in higher dimensions. And this is in fact a result about classification of Fano fourfolds. Now, to recall some definitions, by a Fano variety, a smooth Fano variety, we mean a variety for which the anti-canonical divisor is ample. I mean, taking Fano varieties of dimension at least 3. In this case, the index of a Fano variety is defined as the highest integer r, so that the anti-canonical divisor is numerically equivalent to r times an ample divisor. And note that in this case, numerical equivalence coincide with linear equivalence, and I'll be mostly using this one. Now, recall these two vector spaces, which are respectively the real vector space of one cycles with real coefficient modulo numerical equivalence, and the same one, well, the real vector space of divisors modulo numerical equivalence. And within these two vector spaces, we consider two cones, the cones of effective one cycles and the cone of net divisors, which are convex cones. In this setting, since X is smooth and Fano, the cones are closed and polyhedral, and so they are generated by a finite number of rays. Recall also that given a ray R in the cone of effective one cycles, we can associate a contraction from X onto another variety W, which is a subjective morphism such that the push forward of the structure sheaf of X is isomorphic to the structure sheaf of W. These two vector spaces are dual to each other, as well as the cones within them, and their dimension is the Picard number rho X. Now, consider a prime divisor D contained in X, and take the push forward induced by the inclusion. So the push forward cycles, and then we define as n1 of dx as the image of this push forward. Note that this space here is a sub-vector space of n1 of x, which is generated by the numerical classes of x in X of all the curves contained in D, and that the dimension of this subspace is at most the Picard number of D and at least 1. Now, the
Sorry, I have a question.
Yeah, sure.
Why are these cones polyhedral? Aren't they in general quite messy?
No, they're not in general. I mean, X is a more since it's Fano, it's more in space, and okay. So they are polyhedral. I mean, all the rays are K negative. Yeah, K negative.
Okay. All right. Awesome. All right.
Okay.
Thanks.
Oh, you're welcome. Thank you. The classification of smooth Fano varieties containing prime divisors with Picard number 1 was first introduced by Tsukioka in 2006, where he gives a classification of Fano varieties, smooth varieties, smooth and ORC, such that there exists a divisor contained in X isomorphic to the projected space, where dimension of X is n at least 3. In his work, he also proves that a more general result, that if there exists a prime divisor with Picard number 1, then the Picard number of X is at most 3. In the following years, Casagrande and Druel gave a generalization of this result, and they proved that if there exists a prime divisor D, so that the dimension of the space n1 of the X is 1, then the Picard number of X is 1 or 2 and 3, and X has some contractions onto a smooth Fano variety of lower Picard number. And they also give a full description of these maps of these contractions. Now note that this condition here obviously implies this condition here. In their paper, they also give a characterization of these varieties in the case of Picard number 3. And so they prove that any smooth Fano variety of dimension at least 3 and Picard number 3, which contains in prime divisors that the dimension of n1 of the x is 1, is isomorphic to one of the varieties constructed below. So I have this commutative diagram here. We take two integers a and b, satisfying these two conditions, inequalities, where Iz is an index of Z, and in fact, Z is a smooth Fano variety of dimension s minus 1. So this is dimension, and dimension of x is n, of Picard number 1. And note that these inequalities here imply that the Picard number, the index of Z must be at least 2. Then assume that there exists a smooth hypersurface in the linear system of OZ of D, where OZ of 1 is the generator of the Picard group of Z, so that this is isomorphic to peak of Z. Then pi is a projectivization, it's a P1 bundle of this rank 2 vector bundle Z plus of Z of A, and then take two sections gy and gy hat with number bundles respectively OZ of minus A and OZ of A. And actually these two sections correspond to a surjection of the vector bundle onto either one of the two summons. So then sigma is the blow-up of y along a codimension 2 subvariety S, which is given by the intersection of gy hat with a preimage of A. So S is isomorphic to A. And then set E, the exceptional divisor, G and G hat the transforms of gy and gy hat. And then E hat is the transform of the preimage of A. Note here with the drawing, I mean, I put all these four divisors. They are quite relevant, and we know that, for instance, G and G hat are not do not intersect. So keep them in mind. I will use them as then later. The composition of these two maps, phi is a conic bundle, flat morphism whose fibers are plane conics. And then by the construction, we see that A is a discriminant divisor, that is the locus of Z whose fibers are singular, and that E, the union of E and E hat, is actually the union of all the singular fibers. Moreover, Casagrande and Ruel in their work gave a full description of the cone of factoring 1 cycles, and so we know all the contractions of X. My work consisted on giving a classification of these varieties in the case of dimension 4, and Z then is a smooth Fano threefold with Picard number 1 and index at least 2. Now, this was possible thanks to for two reasons. First, it's of course the characterization result above, and the other is that we have a full classification for smooth Fano threefolds. And so here is the list of all the admitted, the possible Fano threefolds. Now let's take as well another divisor, effective divisor H in the linear system of OZ of 1. We need to assume, well, we need to verify that there exists A smooth in the linear system of Z of D. Now, of course, for these varieties here, this is true because by looking at the table, the H is free. And so this condition is verified by Bertini's theorem. As for Z1, which is this hypersurface of degree 6 in the weighted projective space, the H is not free, it has a base point, but by result from by Skorsky and Prokhorov, we have that although H is not free, a general element in the linear system is again smooth. Also know that by the inequalities A, D minus A less or equal than index of Z minus 1, when Z is, when the index is 2, then we have also D can just be either 1 or 2. And since we know basically anything on these varieties, we also know that 2H is free. And so again, the condition is satisfied. Now, when you count up all the possible choices of A and D, you end up with 28 families of smooth Fano fourfolds. And so the main result in this work is this classification result, where we prove that there are 28 families of Fano fourfolds with Picard number 3, which have a prime divisor, so that the dimension of n1 of the x is 1. These varieties have all index 1, and within them, 22 families consist of rational varieties. For other 4 families, the very general member is not rational, while for the remaining 2, we actually don't know. And then I studied the linear system of the anti-canonical divisor, which is free, with the exception of 2 families where the base locus consists of either 1 or 2 points. Although the linear system is not always free, a general element is smooth. Now, the first step for the proof of this theorem was to compute the numerical invariance, and we start by the Hodge numbers. Now, I used the Hodge polynomial EX, which is this polynomial in 2 variables whose coefficients are the Hodge numbers, since it behaves really well with respect to P1 bundles and blow-ups. And so we see that we can describe all the Hodge numbers of X by knowing basically the Hodge numbers of Z and the Hodge numbers of S, where I recall S is isomorphic to A, and A is just a prime divisor in Z, so it's not difficult to compute the Hodge numbers of A as well. Note that the Hodge numbers of X depend only on Z and D. The other numerical invariants that I've computed were the dimension of the space of global sections of the anti-canonical divisor, the anti-canonical degree, and the intersection of kx squared times the second surclass of X. And just to give an idea, by Rock and Kodaira vanishing, where we get this formula which contains all 3 of these variants, and by using techniques from intersection theory and ways to pass through P1 bundles and blow up, we were able to compute all the theory invariants, which depend in this case from Z, A as well, and D. As for the base locus of the anti-canonical divisor, to compute it, the main idea was to find special effective divisors within the linear system. So I recall G and G hat, let's say, phi, the conic bundle. G and G hat are the transforms of the 2 sections of Y, Gy and Gy hat. E is the exceptional locus of sigma, and E hat is the transform of the preimage of A. And okay, and H is this effective divisor in offset of 1. Now, the idea is to apply the following computation, let's say. So let's take 2 effective divisor M and N, and we see that the base locus of the sum of these 2 divisors is contained in a union of the base loci. And so basically by knowing 3 effective divisors in the linear system, we can use this technique to compute, in fact, the base locus. So we have 2 cases. Either the base locus of H is empty, and so we see that the base locus of the anti-canonical divisor of X is contained in the intersection of these 3 sets. These come from this divisor, these come from this divisor, and the third one comes from this divisor, applying the technique I just stated. And we see that it's contained in an empty set, and so it is empty, and so minus X is free. For the other 2 cases, well, the other case is when H is not free, and so we are in the case where Z is Z1, the upper surface of the degree system in the Poetic projective space. And recall that the base locus of H is a point while 2H is free. Now, observe that when the index of Z is 2, the only pairs of A and D can be either 0, 1 or 1, 2. And so again, we have 2 cases here. And we see that, again, using the same technique as before, the base locus is contained either in the intersection of the fiber over the base point of H with a prime divisor G, so it's this point here, or in the, well, it is contained these 2 points. which correspond to the point P0 by the isomorphism of G and G hat with Z. Now, by some computation, we see that actually these inclusions here are in fact equalities, and that although this linear system in these two cases is not empty base locus, a general element is again smooth. Now, for the last part, I'll talk about the formations of these varieties, and this was done in order to compute order two numerical invariants. That is the first two cohomology group of the tangent shift of X, which I recall correspond to the dimension of, respectively, the automorphism group of X and the dimension of the base of the Kuranishi family. Now, to recall some definitions, let's take a pointed quasi-projective variety S with point S0. Then a deformation of X is a proper flat morphism, so that the fiber over the point S0 is isomorphic to X. Moreover, when a deformation of X is also complete inversal, it is called the Kuranishi family of X. Now, Kuranishi families do not always exist for all varieties, but note that in this context, X is smooth and Fano, and so by the Nakano vanishing, we have that all the cohomology groups of the tangent shift, apart from the first two, the zeros and the first one, vanish, and in particular, the H2 of the tangent shift vanishes. And so by deformation theory, we know that a Kuranishi family exists, is smooth, and the base is smooth of the dimension the first cohomology group of the tangent shift. So we are actually interested in considering smooth deformations, and so I give this other definition, where we define a smooth family of Fano varieties as a smooth projective morphism F from K to S, where S is an irreducible quasi-projective variety. The morphism has connecting fibers, and such that the anti-canonical divisor of K is Cartier and F ample, which means that the restriction of the anti-canonical divisor to have a fiber XS is ample on XS for S in S. And this actually coincides with the anti-canonical divisor of XS. And so all the fibers are in fact smooth and Fano. Now, the construction of X, as we've seen before, so recall X, we have the blow up and then the P1 bundle, can be repeated also in families. So we take a smooth family of Fano triples with Picard number 1 and index at least 2, G, whose general fiber is ZB. And from G, we can construct actually another family of Fano varieties, a smooth family of Fano fourfolds, F from K to B tilde, where the points of B tilde parameterize the pairs ZB, AB, where I call AB is just a smooth element in this linear system. And so that the fibers of F are the varieties of theorem 1 obtained by this pair. Note that by the construction, within the construction actually there is a surjective morphism from B tilde to B, so that the dimension of B tilde is actually the dimension of B plus these two numbers here. Now, the objective here is to compare this family constructed in such way with the Kuranishi family of a general member. And so we do it in two steps. The first one is this proposition here, which states that if we consider a smooth family of Fano varieties F from K to S, and we assume that the fiber over the point S0 is isomorphic to X, which is one of the varieties of theorem 1 given by Zi, A, and D, then all the fibers of this smooth family are actually one of the varieties of theorem 1, and they belong, moreover, in the same family of X, which is the fiber over S0. To give you an idea of the proof, we can assume that the base is a smooth curve. Then, by considering some results by Cotogni, Fanelli, Svaldi, and Tasin, which revolve around the monodromy action of the first fundamental group of the base onto the second homology group of the fiber with rational coefficients, we can say that by taking a finite total cover of the base, we then can assume that the restriction of divisors from the N1 of K to N1 of XS is surjective actually for all the fibers. Now, the verification of this condition here, of this surjection, allows us to go to the next step. So thanks to a result by Wisniewski, we're able to prove the following. So we have key, the family, and then we consider a relative elementary contraction of key, which is a contraction whose contracted fibers are also contracted by F, and elementary means that the difference of the Picard number is 1. Now, when we restrict this contraction to a fiber, we actually obtain for all the fibers a contraction of the fiber, and vice versa. From each elementary contraction of a fiber, we can build up a relative elementary contraction of key, which restricts to the same type of contraction on all the fibers. So basically, this means that all the fibers of this morphism have the same type of contractions. And as I said at the beginning, we know all the contraction of X. And so this allows us to say that all the fibers have a divisorial contraction, which sends a divisor D to a point, which in turn implies that the dimension of the space and one of the X is 1. Now, by looking at the numerical invariants, which are constant under smooth deformation, we see that all the fibers are Fano, they're smooth and of dimension 4 by hypothesis. They satisfy this condition here. And also the second Betti number, which we can obtain by the Hodge numbers, is 3 for all the fibers. And so there are actually varieties of 3 and 1. But again, by looking at all the other numerical invariants that I've computed, since there are now 2 families with the same set of numerical invariants, we see that all these fibers actually belong to the same family of S0. And so these 28 families do not contain common members. They're all distinct. Now, the second step is to consider when 2 varieties in the same family are isomorphic. So we fix A, I, and D, so that the variety of 3 and 1 are just given by the pairs Z and D. So we consider X given by Z and A, and X prime given by Z prime and A prime. And we see that Z is isomorphic to X prime if and only if there exists an isomorphism on the base, which sends A onto A1, A prime. And so this leads us to some consequences. The first one is this inequality here, which allows us to give an upper bound of the first cohomology class of the tangent sheaf, and by rock also an upper bound of the zeroth cohomology class. And this is true because if we take F bar as the Granici family of a general member of X, and then we consider as F the family we have constructed above, but starting from G as the Granici family of Z, so that the dimension of B is actually the first cohomology class of the tangent sheaf of Z, and so the dimension of B tilde is equal to this number here. The dimension of B bar is actually, since this is Granici family, is this number here. And step 1 states that this morphism, H, let's say, is surjective, but step 2 says that it's not always injective. So in general, we have only this upper bound. There are a couple of examples where we can say a bit more. For instance, when I is equal to 1, 2, 3, and 4, then we have that H0 of the tangent sheaf of Zi is 0, which implies that the automorphism group of Zi is actually finite. And so by step 2, we see that this morphism is not in general injective, but is at most a finite morphism. And so actually this inequality here is an equality. Another special case where we can say a bit more is when we take I equal to 7 and D equal to 1 and 2. Actually, Z7 is just the projective P3. And since hypersurfaces and quadrics in P3 are all projectively equivalent, by step 2, we see that X is rigid in this case. And so H1 of Tx is actually 0. Now, for the last part, we talk about rationality, which we just give a comment. Now by construction, X is given by a blow up and then a P1 bundle onto Z. And so X is P-rational equivalent to Z. And again, by what is known in Z, we can gather some information on X. So whenever X is rational, X is also rational. And this is true when I is equal to 4, 5, 6, and 7. When I is equal 1, 2, 3, and 4, well, just 1, 2, and 3, then Zi is not rational. So we look at stable rationality. Now recall that, just point there, Z is stably rational. If there exists an integer n, such that the product of Z times Pn is rational. And so if maybe we can, by studying stable rationality, maybe we can gather some information on X. And we have a work of Hassen and Zinkel, which comes in help. So as for Z3, this is a cubic in P4, which is not rational, is irrational, but stable rationality is yet another problem. So in this case, we actually don't have any information on X. As for Z1 and Z2, again by Hassen and Zinkel, we have that they prove that the general element in these two families is not rational. And so as a consequence, we have that a general element general X is again not rational. And so this gives us the 22 rational family. This gives the 4 families where a very general is not rational. And the cubic fourfold gives the other 2, which we don't know anything about. And so, yeah, I'm done. Thank you very much.